Hi everybody, today we're going to continue our lectures on optics, and today we'll be looking at lenses. Before we look at mirrors, which work on the principle of reflection, lenses work on the law of refraction, the bending of light as you change media. Now there's two types of lenses we're going to look at. A converging lens, which some teachers call a convex lens, and a diverging lens, which some teachers call a concave lens. Now, one thing that differs a lens from a mirror is that where a mirror only has a focal point on one side, either in real space for the concave or virtual space for the convex mirror, a lens, because light can go either direction through a lens, has a focal point on both sides of the lens. But the converging lens, what it will do is it will take any parallel light rays and converge them together, bring them together. And then it will produce different images based on where the object is located. Now, for example here, this simulation sort of gives you that idea. This is called a converging lens. As you can see, what it does is it takes light rays and kind of brings those light rays together. Now here's our object. And our object is kind of far from the lens. And it produces this image here that you can see is kind of upside down and a lot smaller. But as we move the position of the object closer to the lens, notice that the image grows larger, though it still remains upside down. And then we kind of get to a point where actually our image seems to disappear off the screen for a moment, and all of a sudden it appears behind us, again, much larger. Now, one of the interesting things to understand about a lens is even though there are two focal points, okay, generally as a rule, whatever side the object is on, we consider that to be the real space side for the object. But for the image, its real space is on the other side. Okay, so the object is in real space and the image is in real space. And that's because the light makes it through the lens. Okay? However, if the light doesn't make it through the lens, and we'll see how that happens, in other words, the image appears here on the same side of an object, that's considered a virtual image. Okay? And you'll notice something that maybe we saw with mirrors. Notice that all our real images tend to be inverted upside down, and all our virtual images tend to be upright, right side up. Okay? So the tricky part with a lens. With a mirror, I mean, we had real space and we had virtual space. But with a lens, the image, real space, is on the other side from the object. Virtual space, or virtual image, will appear on the same side as the object. Keep that in mind. So again, here we have a converging lens that has a focal point on both sides of the lens. Now again, what happens with a converging lens is when we have these parallel light rays, that run parallel to the principal axis. Well, because it refracts or bends the light ray, it's going to bend it so that it passes through the focal point. In other words, it's going to converge or bring those light rays together to make them pass through that focal point. Okay? So this is your typical kind of magnifying glass, where maybe if you played with, you can take sunlight and focus it to a very, very sharp point. Now, we can draw ray diagrams for lenses just like we did for mirrors to locate and determine things about the images that are formed. Now, again, I like to focus on the same sort of rules, C and F. But for the converging lens, and later the diverging lens, it's hard to see a C. There's only a focal point. Well, the C is located actually in the center of the lens. Okay, C is in the center of the lens. So those would be my 2 points to focus on, the center of the lens and the focal point. So my first ray, like always, from the top of the object through C, where now C is at the center of the lens. And then my second rule is still the same. I draw a line from the top of the object straight across, parallel to the principal axis, then down through the focal point. And then depending on where the light rays cross, that's where my image will form. Okay? So let's take out array diagrams and look at examples. Okay, so here's our first converging lens ray diagram, and you'll notice I've marked the focal points, and I've also marked twice the focal point, the same idea of what would have been C for the mirrors. And we're going to look at our sort of 5 different scenarios. First one starting off when we're kind of far from the lens, beyond 2f. Okay, so let's draw a ray diagram. So our first ray, we want to draw from the top of the object right through the center of the lens, okay, through C. Our second ray, as usual, starts off at the top and runs parallel to the principal axis. Now, it's a converging lens. I need to bring or converge the light rays together. So the focal point I want to go through is here in the front. I want to go through F and bring those light rays together, converge them. And now my image I draw from the principal axis to the point where they intersect. Now, let's look at that. Because the image is on the opposite side of the lens, it's a real image. Clearly, it's inverted. It's upside down. And if we were to measure the size of it, we would find that it is a reduced image. It's smaller. In other words, it has a magnification less than 1. Okay? So that's our first example. In our next one, we've put it right at 2f. Now, that's kind of a tricky one because there is an exact answer for this, turns out, for this particular one. But again, if I draw my ray diagrams, my first one, right through the center of the lens, and now my next one, this is the tricky part, getting it perfectly parallel. And if you draw then converging the light rays, if you converge them in the right way, so you go down right through the focal point, then the image actually forms right here, also at 2f. Okay? Now again, the image is on the opposite side of the object, so it's a real image. Its orientation is still inverted, upside down, and it's actually going to be equal in size. Okay? A magnification equal to 1. Those heights are equal. The height of the object and the height of the image are the same. One of the things we'll sort of see later on is that this distance that we called s, the object distance, and this distance here, s prime, are also equal. Okay? And that's what makes everything kind of equal on both sides. Trying to get it? Okay, now we've moved closer to the lens. We're between f and 2f. So let's draw our ray diagrams. First ray from the top of the object through the center of the lens, C. Second ray, parallel to the principal axis, straight across. And then this one, when we want to converge the light rays, go down through F. We find our image is beyond 2F on the other side. It's on the other side of the object, so it's real for a lens. It's still inverted. Notice that that real and inverted keep going together hand in hand. And here it's enlarged. In other words, a magnification greater than 1. All right, the next one. This is interesting. We're right at the focal point. Okay? Let's draw our ray diagrams. First one from the object through C, the center of the lens. Second ray, straight across. And then when we go and try to converge by going down through F, what we end up with is a set of parallel lines. Okay? And parallel lines can never cross. And if they can never cross, there is no image formed at all. When we're right at F for a converging lens, there's no image formed at all. Last example, between the focal point and the lens, inside F. Okay, let's draw our first ray, top of the object through C. Second one runs parallel to the principal axis. Try to converge it through that focal point. And we find the rays don't intersect, but they're actually not parallel. So when they're not parallel, what we do is we kind of start finding out where they do intersect by drawing the lines backwards from the original line. And we find that it does intersect on the same side as the object. Now remember, for a lens, if we end up with an image on the same side as the object, it's a virtual image. Also notice it's upright. That's sort of one of the other guys that is probably virtual. Virtual and upright tend to go hand in hand. And it's clearly enlarged. Okay. Magnification greater than 1. Okay. Now, there's some interesting things that kind of happen here if you really take a look at it. In the case where we are beyond 2f with the lens, we got the same type of image when we were beyond C. The same thing as 2f as the concave mirror. What we can also see is that when we had our object right here at 2f on the converging lens, it matches the same type of image formed by the concave mirror when we were directly at C. Again, same thing as 2f. And that process sort of continues on. The same type of images that were formed with concave mirror were also formed with the converging lens, including the idea that when we were right at the focal point for either one of these, the concave mirror or the converging lens, there was no image formed, and that when we were inside the focal point, we got a virtual upright image. So that's basically the idea of how to determine images using ray diagrams with a converging lens. The next type of lens is called a diverging lens. Now, where a converging lens brings light rays together, a diverging lens tends to spread them apart. Again, because it's a lens, there's a focal point on both sides. Now, where the focal point is considered a positive value for the converging lens, it's considered a negative value for the diverging lens. We'll sort of see what that means here. So with a diverging lens, where again the focal point is on both sides, okay? Well, if we again bring in our parallel light rays that are parallel to the principal axis, well, where the converging lens would converge or bring the light rays towards that positive focal point, a diverging lens spreads them apart, diverges the light rays, and so it makes them appear as if they were originating at the front, which is considered a negative focal point for the lens. So as you can see, instead of converging the light rays, it's diverging or spreading those light rays apart. So how do we draw our ray diagrams for this? Well, we're going to follow the same set of rules, okay? C and F. Now, this lens has always been the trickiest one for people. I don't know why, but it is. Our first rule is we draw a line from the top of the object through C. And for a lens, C is in the center of the lens. Okay, so we're still drawing that ray. Our second rule, from the top of the object, straight across, parallel to the principal axis. Now, it's a diverging lens, which means we've got to spread those light rays apart, not bring them together. Okay, and it doesn't reflect, it refracts. So the light ray has to go through. So what ends up happening is it gives the appearance that the light ray is coming from that front focal point. And so my image forms right in here, where these rays appear to cross. Now, it's on the same side as the object, making it a virtual image. It's also an upright image, and it's clearly reduced. Magnification less than 1. Okay? That's our first example. In our next one, we'll move right at 2f. Okay? So, draw our rays. First one from the top of the object through the center of the lens, you see. Second one, straight across, parallel to the principal axis. It's a diverging lens, so we want to make the rays diverge, spread apart. So if it comes from that front focal point, here is the intersection location. And notice I'm getting the same image again. Virtual, upright, and reduced. Well, guess what? The only type of image that a diverging lens can produce is a virtual upright reduced image. It can never produce a real image, okay? Which is why all cameras, movie projectors, everything like that must use a converging lens so you can actually see it on a screen. A diverging lens would never allow any image to appear on a screen. So this is the only type. But that's just like the convex mirror. If you remember, the convex mirror, which also spreads light apart when it reflects the light, can only produce virtual upright reduced images. Okay? So what we're seeing is that the converging lens and the concave mirror produce similar images. The diverging lens and the convex mirror produce similar images. Okay? Now, I'm not going to do the rest of these diverging pictures for you, but I highly recommend that you do them and practice them. Okay? It can only help. So that's basically the idea of ray diagrams and how you do them with lenses. Okay? Next time we'll focus on the math, how we can sort of calculate all this stuff. All right, see you next time.